theme of sustainability and among other things, resiliency and I think climate change. So tonight's talk will, I think, dovetail well with the theme this fall. The invitation for abstracts is still open, and we would invite any of our members or listeners to submit abstracts. The request for abstracts runs through June 7th. But I would very much encourage somebody who's interested to submit an abstract and or just plan on attending. The national meetings are a great opportunity to network, to meet people from different sections. And then one of the highlights are the different field trips that are offered as part of the national meeting. So now transitioning from our short section business, I want to introduce our speaker tonight. Ian Gosttschalk is a geophysicist who did his undergraduate education here in Illinois at Wheaton College, graduated in 2015. And he then pursued a PhD in geophysics at Stanford and I can't say the word, graduated last fall from Stanford. His areas of research interests are hydrogeophysics, saltwater, intrusion, and rock physics. I like your listed hobbies, Ian, of backpacking, woodworking, and ultimate frisbee. But Ian tonight is going to share from hopefully an applied geology perspective, highlights or a basic description of what is hydrogeophysics. It's really an exciting area of a new tool for groundwater mapping and studies that I think started in Europe and then is migrating to the US. Its beachhead is in California, but I understand it's now being applied in other areas. I saw an announcement recently, the Wisconsin survey was doing something. So I think this is a tool of the future, and I'm excited to learn more. So with that, Ian.
Great. Yeah, thanks, Dave. And thanks everyone for having me. I'm excited to just go through, as Dave mentioned, some of the applied geology perspectives on this, what's really an exciting, actively developing geophysical method called airborne electromagnetics. Before I jump in and show my presentation, just a couple notes. Feel free to ask any questions throughout. I think the mechanism to do that is through the chat. And I believe Anna is going to be monitoring the chat, and at various points, if there are a couple questions that pop up, she'll chime in and ask the question.
Yeah, will do. And feel free to use the raise hand function too. I'll keep an eyeball on that if you want to just chat a little bit.
Okay, perfect. And then also, if you could, if you don't mind muting your mics while we're doing the presentation, just in case some feedback comes in and out, that would be fantastic. And so with that, I will jump in. Can everyone see my screen okay?
Yep.
Awesome, fantastic. So as Dave mentioned, I am a geophysicist working at AECOM. Previously, I was at Stanford University. I was researching hydrogeophysics, this intersection of geophysics and hydrogeology. And it really is an exciting field because, as I'm sure we're all aware, our world is becoming more and more interdisciplinary and more interconnected as we're finding new research avenues that cross different boundaries, cross different research areas. And so this really dovetails nicely into this geophysical method of airborne electromagnetics. which is becoming more and more popular every single year. We're seeing surveys going on across the world. In the US, every year there are more surveys. As I'll give you a glimpse of some of the applications and the surveys from within the US and across the world. And so what I'm hoping that you can get out of this talk today is just a greater familiarity with this method, how it can be applied, its pros and its cons, and maybe you can think about through this talk how these AEM data, the airborne electromagnetic data, could be used for an upcoming or existing project that you're working on, or some research that you're working on, or a client that you're working for. You know, you might not be interested in planning a full airborne geophysical survey from start to finish. There's a lot of logistics that goes into that. But because these surveys are happening more and more across the US and they tend to be funded by public agencies, you may have the advantage of being able to rely on these data for an interpretation as another data set. So that's my hope of what you'll be able to get out of this talk. Again, we have a small group and it's casual, so feel free to stop and ask questions, because I'm hoping that this can just be educational to some degree. And then before I really get into the meat of things, I just wanted to pop this up really quickly and say, you know, it's good to be back at AIPG. I, during my undergraduate, was a student member of AIPG. And during my undergrad at Wheaton College in Illinois, I actually did some research, some lab research in hydrogeophysics, working with tanks, two-dimensional tanks, simulating groundwater flow and measuring electrical resistivity. And I wrote up the results and submitted them to the professional geologist back in 2013, 2014. And so it was actually displayed in one of the student volumes of the professional geologist. And, you know, that was such an exciting thing for me when I was starting out my scientific career. And, you know, that was my first scientific publication. And so, you know, it's just, AIPG is a fantastic organization. And, you know, I would just recommend to any students who get to hear this that you invest in AIPG and stay involved. It's a fantastic network and group of people who are there. There's a lot of mentorship opportunities there, and as evidenced here, you can even pursue some scientific exploits. So it's really cool, and thanks for having me back. So just to start off at a broad scale before we narrow down our focus into this airborne electromagnetics and how it can be applied. So geophysics in general, you might ask yourself the question, why would you want to collect these data? As geologists, we often feel much more comfortable with some dirt that we can rub between our fingers, or being able to look at an outcrop itself. And you know, geophysics plays a really important and crucial role in broadening our understanding and really interpolating between the locations where we have good understanding of what's in the subsurface. This cross-section here is just kind of a schematic of that, where on each of the ends, you might have a borehole where you have a good understanding of the subsurface. You have a detailed understanding of the stratigraphy. But in between, you really might not have that much. That's often the case, at least where I've been working in California, where there's fantastic information in a few distinct locations, but between those two locations, there may be a fault zone, or there may be, you know, it might be an alluvial aquifer where clay layers are pinching out and then reappearing. And you're really not sure how to connect the dots between borehole A and borehole B. And so that's really where geophysics comes in. Traditionally, people have done surface geophysical surveys where you might plug in a few electrodes into the subsurface and generate a current, or with seismics, create some pulse of energy that you then listen for in another location. And so the geophysics, it allows us to fill in those gaps. And that's why it's so applicable to almost every space in geology, is because we always want to know more about the subsurface, and geophysics helps us do that in a spatially continuous way. And now zooming in more to this airborne electromagnetic method. So I told you that it's being actively developed. It's an exciting and powerful method. And the question you might have is, well, why is it so popular or powerful? And also, why recently is it popular? And I think you can distill this into three major advantages that this method has to offer. And those would be the coverage, or the spatial coverage of the data, how much data you can collect over a mapped region. Then the depth, which is to say that while you're covering a large area, you can actually see down to quite deep. And then finally, the property, which is the physical property, electrical resistivity, which is what you map and estimate when you collect airborne electromagnetic, or AEM, data. And so going a little bit more into depth in each of these. So with coverage, when you're collecting these data, you can collect up to 600 miles of data in acquisition every day. That's an upper, kind of an upper threshold if you really have no barriers while you're flying around. But that's absolutely incredible in comparison to any kind of ground-based method, where you might get a few transects of, I don't know, half a mile in a good day's work, depending on what the method is and how mobile it is. Secondly, you can access difficult terrain. Oftentimes with ground-based surveys, there might be barriers, there are trees, rocky terrain. It's difficult to stick electrodes into the ground just because the ground is very dry and you can't get any good surface conductance. Those aren't issues with this method because there's no contact with the ground. It's an airborne method, which is, as you can see from this picture, usually towed beneath a helicopter, and in some cases attached to a fixed wing aircraft. And then finally, land access. You don't really have land access issues here. You don't have to request permits to enter onto someone's land because you're actually flying in the airspace. So you do need to submit a permit to the FAA to request that you can fly there. And of course, you have to obey FAA regulations. You can't fly over military zones, and you can't fly over buildings, but you don't need to worry about flying through somebody's field, which can honestly hamper a lot of geophysical surveys if you have one landowner who doesn't want to give you access. With depth, I mentioned, while you're flying around and collecting, up to 600 line miles of data per day, you're also seeing down extraordinarily deep, considering that how quickly you're collecting these data. So you can image down to about 1,000 feet below the ground surface while you're doing these data acquisitions. And then finally, the physical property resistivity, as I mentioned, it's a very versatile geophysical property to measure. And that's because it can be related to so many material properties of interest. As we'll see later, and I'll get into some more detail, this can be related to the salinity of groundwater. It can be related to the sediment texture, or the how much clay is in the subsurface. It can be used to identify massive sulfide deposits. There are many controls on the resistivity of the subsurface, and for that reason, you can apply these surveys in many different ways. And so for those three principal reasons, I think that the AEM method is grown in popularity, and that partnered with the accelerating advances in the censoring that have to take place. We need very accurate GPS measurements and measurements of the tilt of the transmitter, and a lot of coordination of logistics in order to just collect high quality data. And that technology is only developed relatively recently. So you partner these strengths with the developing technology, and you can see why this method, okay, this is why we're now starting to see a lot of these surveys across the world.
Hey, Ian, I see Harvey has chatted in. Can you see the bedrock sediment interface well?
I will show an image in just a few slides that shows exactly that. It really depends on whether that interface is shallow enough for you to image. So in the Central Valley of California, where bedrock can be 2,000 feet below the ground surface, you won't be able to see it. But if it's shallower than that, oftentimes you can, because the bedrock tends to be, especially if it's granitic, is much more resistive than the sediment that's on top of it. So this is an image that oftentimes people will show just to demonstrate the different controls on the electrical resistivity. So here you can see this is grouped into on the y-axis different geologic properties or types, and then on the x-axis you can see resistivity up on the top, and then its inverse, the conductivity, on the bottom. And so you can see that up in the top left, there is you can see that massive sulfides have an extremely low resistivity. You can see in the next row down, different weathered layers, differentiating between mafic and felsic rocks. I haven't used resistivity to do that so much, but what I have done is identify differences between clays and gravels and sands, which is in the third row here. Sedimentary rocks, again, you can pull out the clay content, or how clay rich a rock might be. And then finally, in the bottom row, you see the water. The main control here is the salinity. You can just think, if electricity, if it's easier for electricity to flow through this rock fluid mixture, that's going to change, by definition, the resistivity of the subsurface.
And Ian, we also had another question. How high does the helicopter fly for the survey?
Yeah, great question. So it's actually a very low flying helicopter. The helicopter itself sits at about 200 feet of altitude. And then the transmitter, that loop that you see here hanging below it, that is about 100 feet below the helicopter itself. So that means the transmitter's hanging at about 100 feet altitude, ideally, because the closer to the ground you get, the better signal you have. However, if there are obstacles in the way, you obviously can fly up above those. Once you get above about 180 feet or so, you don't really want to keep those data because they become so noisy. So just to give you an idea, and this will kind of show you how the AEM method works and really brings our understanding in here. But coming back to these two boreholes that we have, our idea of using the AEM method is to really fill in these gaps here. And what we'll end up with is some kind of grainy image of the subsurface that we have to interpret still. The AEM method hasn't done all of the work for us, but it gives us a really good reference point to extrapolate beyond and interpolate between different points where we have good, distinguished lithology and subsurface understanding. A little bit more, now I'm just going to jump into the physics of this measurement so that you can get an understanding for that. What happens is, as we're flying this helicopter around, this is with our imaginary subsurface down shown in the gray below, and our imaginary tree that's not to scale, as my advisor always liked to say, to the right. As we're flying around, we apply a strong current to this loop, this big transmitter loop that you see hanging below the helicopter. Now, when we allow that current to flow around the transmitter loop, it establishes a magnetic field in the subsurface, shown here in those dashed lines. And then what we do is we very quickly, rapidly shut off the current that's flowing around the transmitter loop. And that causes the primary field, the primary magnetic field, to decay. And what happens there is it sets off a kind of electromagnetic chain reaction where there are some electrical eddy currents that get induced in the subsurface. And then in turn, because those themselves are decaying, they create new secondary magnetic fields. And that's what's measured back on the receiver. So the receiver that's that's located close to the transmitter is sitting there, and it's listening for a voltage that's induced in its coil. And effectively what we get is we get a signal with time then, which we can then backtrack to get information about the resistivity as a function of depth. So, that's all, it's a lot there to take in, but the really important part is that the signal that we acquire, we're able to backtrack and estimate what the electrical resistivity is with depth. And so this resistivity, I'm just showing you this scale here because it's the common scale that I'll be using in a lot of the slides coming up. As I mentioned, there are quite a few controls on that resistivity, and the primary ones that we'll be looking at are here. So what could decrease the resistivity and push you farther into the red zone could be an increase in salinity. It could be an increase in the clay content. It could be an increase in the water content, or we won't touch on this too much because I haven't hit upon it in my research so much, but certainly it would be the case if you're in those types of areas that increasing metallic content, for example, within ore deposits would also decrease the resistivity significantly. And it's important to also remember that what we get out of this method is one estimated value of the resistivity at a certain depth. So from that, we need to somehow disentangle the different potential influencing factors, the salinity, the clay content, the water content. And that's why it's so important to acquire good existing data, good auxiliary data, so that we can get the best possible interpretation out of the resistivity. Because without those, there's no way to say, without some other understanding, there's no way to say whether a decrease in resistivity is attributed to exactly one of these potential influencing factors.
Hey, Ian, a couple more questions
Great.
on that. One about ground truthing results. Do you have any ground truth results to the subsurface along a cliff or tall vertical exposure of soil? And another question, what type of ground/borehole control do you need to help in the interpretation of the airborne geophysical results?
Yeah, both great questions. So the answer is, you really do need some kind of ground control. Otherwise, you won't be able to disentangle these. You'll see in a few places, as we get into some more detailed cases, where you'll be able to see the ground truth. You'll be able to see the subsurface information that we had existing before the AEM survey, and that's what we use to interpret the AEM data. In general, when flying these kinds of surveys, what we're starting to recommend is that people have at least two boreholes containing lithology, good lithology information per square mile or per public land survey section. So that really helps you understand on a relatively fine scale what's going on. In California, it can sometimes be a struggle to find two good boreholes per square mile, but things might be a little bit different and perhaps a little bit better in Indiana and Illinois. And then certainly you want good measurements of the water level that are recent around the time of the AEM survey. And if it is a known issue, you would like to have, or if you know that the salinity varies spatially in your region, you should know what the spatial distribution of salinity is, because that will have a strong effect on the AEM data. And so now I'd like to just go through a few applications of this method across the world. So there are surveys that are going on that are both international, they're domestic. There are some that are absolutely massive statewide scale that I'll show you a couple of them to you. And then also ones that are more modest in size at the sub-basin scale. So I try not to say small scale because these are still by nature large scale applications. because you don't want to plan all the logistics for a helicopter survey for just flying across a field. It wouldn't be cost effective or time effective. And also the resolution of this method is not really, it's not applicable to very, very fine scale applications. So your resolution starts at about 6 feet or so. The absolute best resolution that you have is near the surface. It's about 6 to 10 feet, and then it decreases in the resolution decreases with depth. And so these sub-basin scales are still relatively large scale. And they've been used to support groundwater management, environmental resource management, and mineral exploration. So I'll show you a few of those cases here. And again, feel free to stop me with any questions. And so starting with some of these local or local to you all, not to me at the moment, I'm in California, but these AEM studies. So first of all, in the southwestern Lake Michigan, in just 2018, there was flown an AEM survey, and that was conducted by the Illinois State Geologic Survey. And their approach here and their goal was to map the distribution of beach sand along the southwestern Lake Michigan coast. And you can see on the right-hand side an image of the flight lines that they flew. So all those green lines are where the helicopter actually flew. And then on the bottom left here, you can see a cross-section of the resistivity of the subsurface, and then printed on top some of their interpretations of what existed there. So you can see in this case, this purple blob, which is, I believe, a very high resistivity in this case, is the bedrock, is the dolomite bedrock. Also relatively not in Illinois, Indiana, but just north in eastern Wisconsin, the USGS is actively mapping out the depth to the Silurian bedrock, and that's to inform farming practices. And so this survey has been going on in 2021. I've seen maps of the flight lines in Door County from January, February this year. And the idea was exactly to the point of one of the questions we got earlier, which is whether you can see the bedrock interface. And you certainly can, especially if it's shallow. And this can be a really good way to get a regional scale map and a uniform data set to estimate something like that. And so this method really helps with creating regional unified data sets, where oftentimes you might have to compile something between many different agencies. Moving over closer to where I am, in California, there have already been multiple independent surveys conducted by Stanford University, conducted by the California DWR, and by others. This is here another image where you can see a resistivity section. And on the far left-hand side of the resistivity image, you can see the bedrock, which is part of the Sierra Nevadas. And then you can also see what's been interpreted as various faulting activity that's going on, and actually creating hydrogeologic barriers in some locations. And the local groundwater management agencies wanted to cite some locations for potential infiltration for recharge. And so that's yet another application of this method. Moving across the Atlantic Ocean in Denmark, which has pioneered a lot of these studies, just because where a lot of the science has been developed out of Aarhus University. The map in the bottom left is a spatial coverage map of where they've flown AEM surveys. So you can see at this point, I think it's beyond 50% of the land area of the country of Denmark, which granted is not a large country. It's not much larger than the state of Maryland, but it's still very significant to have that much coverage. And in the bottom right image, you can see where they've used these data to identify glacial sand channels that are in this kind of bright red color.
Hey, Ian, we had a question. Which basin is the California example from?
This is in the Indian Wells Valley. I'm sorry, I wish I had a map up for you. So there are many surveys that I know of across California, both in the Central Valley, in the Salinas Valley, in Indian Wells Valley, and this one specifically is from Indian Wells Valley. Then we have over in Australia, this is the largest AEM survey or set of surveys in the world at the moment. It is, the goal is to acquire AEM data across the entirety of Northern Australia, about just under 400,000 square miles of area that they're covering with these surveys. And below is just one flight line that you can see on the x-axis ranges about 150 kilometers. So it is just an absolutely enormous survey. And the purpose of it is multifold. It's to enhance geoscientific information available, support resource exploration, provide existing data for groundwater managers. And so it's just seen as a baseline national data set that they would like to have available to the public. And then in California, this is another large-scale survey that the Department of Water Resources in California has undertaken, that I'm lucky enough to be a part of through some of my work. And the goal here is to support sustainable groundwater management and really address basin-specific needs. And these AEM data are going to be acquired in all medium and high priority basins in California, which are all of the groundwater basins that are in this this peach orange color in the map. So I would guess, don't quote me on this, but I would guess that it's about 1/5 or maybe a little bit less of the area of California. So it's also a significant undertaking. I believe the biggest AEM survey in the US and one of the biggest in the world.
Ian, we had another question come in. Are you aware of any AEM surveys in Southern California along the coast to map saltwater intrusion? And then also, several more coming in. What is the budget for the Central Valley program? And can this be used to identify areas of increasing salinity in shallow aquifers due to ag water use?
Trying to go in order here. So in Southern California, there have been data collected in Pismo Beach, if that's considered far enough south. I don't believe there's been anything collected farther south than that. Also in Paso Robles, close to San Luis Obispo, there's been data collected in Southern California. But then all of the basins that are shown in this peach color will be flown in the upcoming 3 years through this DWR program. The budget for the DWR program is $12 million to collect data across the entirety of California over the next 3 years. And so it's a big undertaking. And similar to the Australian project, it's really seen as a statewide resource that groundwater management agencies are able to rely on these data to develop their groundwater models, to develop sustainability plans going forward. And so it was seen by the California legislature as an important project that they wanted to fund. Did I miss any of the questions? Did I get them all?
It's related, but the last one was specifically, can this be used to identify areas of increasing salinity in shallow aquifers due to ag water use?
Right. So theoretically, I would say due to ag water use specifically, I don't believe you would be able to, because the elevations in the total dissolved solids is actually relatively small. It's large enough that it can make water too saline to drink, but it wouldn't necessarily be detectable by the AEM method. The change in resistivity would be pretty small. You'll see, we'll go into a case of my research in the coast, and there you will see, once you get into percentages, 5, 10, 50% the salinity of seawater, then you start to really see the effects due to salinity. But just from ag water, from nitrates and things like that, it would be it might be difficult unless there's significant accumulation. So what I would like to try to do now is jump into a case study. So instead of talking about generalities, go into the specifics of how I was able to use the AEM method and these data to support coastal groundwater management, and that's in the Salinas Valley in California. And so if we have time, we'll go over both of these points, but certainly we'll start off with the first one and see how we are, how we were able to use AEM data to map out the distribution of saltwater and fresher water in the Salinas Valley, and how we're able to make some interesting interpretations of the hydrogeology in the area. So to continue setting the scene a little bit, all of those basins that you saw in that peach color in the earlier map, those were all considered medium and high priority basins. And so a subset of those are these critically overdrafted groundwater basins in California. And so these are basins which have continually lowering groundwater levels in their basins and have been deemed by the California DWR as not being sustainable. And so we see that this is a big problem in the Central Valley, which is this the central region here in California, where you see the largest body of purple. But you also see a subset of these basins that are along the coast here. And you see that there's a very special and unique problem that are faced by these coastal basins, which is saltwater intrusion. So this critical overdraft also feeds into saltwater intrusion and exacerbates it. So saltwater intrusion is the landward incursion of saltwater into terrestrial aquifers. And it's a natural process. It happens in most locations where you have a coastline and an aquifer that's inland. And just due to the density difference between saltwater and freshwater, it's about a 2% density difference, but that density difference allows the saltwater to build up a larger pressure and force its way inland, especially as you go deeper and deeper in elevation, creating this what's known as a saltwater wedge that forces itself inland. But it is a natural process, and it just reaches a natural equilibrium at a certain point where the saltwater wedge doesn't move any farther inland. However, when we reduce the inland pressure side by pumping too much and decreasing groundwater levels, that allows the very constant pressure of the ocean water to intrude even farther, which is what I'm showing here by this lowering groundwater level. And this well that's pointed out here, where before it was pumping out relatively fresh water, now all of a sudden the bottom of it is is intersecting the saltwater interface. And so it's a very important thing for groundwater basins, coastal groundwater basins, to understand the distribution of saltwater and salinity in the basin, as well as to project what the saltwater interface will look like. And in order to do that, most people go to groundwater models, because that's what allows us to kind of project into the future based on some knowledge. So these numerical models, there are numerical models developed for saltwater intrusion that take into account the variable density of the subsurface water. And the problem with a lot of these models, or really any model, is that it relies on data in order to calibrate it. However, as we've pointed out before, oftentimes we don't have enough data to accurately and well calibrate a model like this. You might have boreholes that are relatively sparse spatially, and so the model itself, you might not be able to rely on or be able to accurately use to predict what the salinity is with time. And so our approach here, in this case, was to unify both these numerical groundwater models and supply the data that's needed to calibrate them using airborne electromagnetic data, along with borehole data and other auxiliary data. And so the first part of that process was to look into our study area here, which is in the coastal Salinas Valley. As you can see in the zoom up, it's right next to the Monterey Bay area. The groundwater levels in this region have been continually decreasing over the past decade or more. And it's getting to the point that seawater intrusion has been coming into this basin over 6 miles inland to the city of Salinas. So it's an extreme problem that really needed to be addressed. And the first step of that was to map out where the saltwater, where was the saltwater and where was the fresher water in this basin. And here you can just see a little bit more about the geology. We're situated in between the Gabilan Range and the Santa Lucia Range in California. And there is a fault zone running along the south side here. Now zooming in even more to the study area, you can see this map. Still, the Monterey Bay is on the west side of the map. And I have this dashed line transect running from north to south here. And our understanding of the hydrostratigraphy here in this area is shown in this cross section on the right. And so that kind of runs along the dashed line. And in our cross section, north is on the left and south is on the right. And so here you can see that there are 3 main aquifers: the dune sand aquifer is the surficial aquifer on top, the 180-foot aquifer below, and then underneath that, the 400-foot aquifer. And here our existing understanding of the extent of saltwater intrusion in the 180-foot aquifer, that middle aquifer, that's shown as an orange contour here on the map. And so that contour was created using borehole data collected by the county. So they produce these maps every couple of years, and this was their understanding of where the salt water was at the moment. Then below it, in the 400-foot aquifer, you see that contour here in pink. And as you can see in the 400-foot aquifer, the extent of saltwater intrusion wasn't as severe as in the 180-foot aquifer, but we did start to see these little pockets, these little islands of saltwater. You can see 3 different islands here where saltwater had just started appearing in the 400-foot aquifer. And that had started raising the suspicion that there might be some connectivity between these 2 aquifers, and it was allowing saltwater within the 180-foot aquifer to find these pockets or these locations of connectivity and flow downward into the 400-foot aquifer, kind of short-circuiting the whole system. That's signified here as like this little red arrow going down. Then at the same time, to make things more exciting, there was found a pocket of fresher water in the surficial dune sand aquifer on top. And then some fresher water was also found in the 180-foot aquifer below. And the mechanism for this has been documented as what's known as passive active saltwater intrusion. The term itself doesn't matter so much, but the idea here is that fresh water would enter the dune sand aquifer through precipitation. And because of the gradient of groundwater flow, that water would flow toward the ocean. And then it would, at a location where the aquitard separating the dune sand aquifer from the 180-foot aquifer would terminate, that water could then drop down into the 180-foot aquifer. But then because of the groundwater gradient in the 180-foot aquifer, it would then start flowing inland. So it did this quite interesting and unique flow toward the ocean and then drop in a 180-degree turn coming back inland, and it would flow along with the saltwater. It would kind of surf on top of the saltwater below it, both of them coming inland. It was a really unique area, and we wanted to explore and understand more the distribution of this fresher water and also the distribution of the saltwater in this area. And because these maps were drawn just based on the existing understanding using borehole data. We really wanted to get a better, denser understanding of what was going on here. And so that's why we turned to the airborne electromagnetic method. Right here, you can see the locations of all of the flight lines of the AEM data. And you'll see that there are quite a lot of little jumps and just small lines that are disconnected. And that's because what I'm actually showing you here is the data after we process them and remove some locations due to noise. And
question, Ian.
Oh, great. Yeah.
It sounds like this could be used to track changes in salinity due to saltwater intrusion over time. Are there plans to do multiple surveys to quantify these changes in addition to providing data to calibrate groundwater models?
Great. Yeah, that's an awesome question. And I think theoretically, yes, you can use this method for exactly that. And it's a great thought that we've had. I think in practice, you have to have a pretty extreme case of saltwater intrusion, of actively developing saltwater intrusion where the front is changing rapidly over time in order to see that actually come out in the data. And based on some just back of the envelope guesses, I would say that you wouldn't, even in a case as extreme as we're seeing here in the Salinas Valley, you wouldn't want to do a repeat survey in less than 5 years. But I think something like a 10-year update in a location like this could add enormous value for monitoring and for calibrating models. I will give just a really quick aside about these planned flight lines, just because this is a more applied crowd that you might find this to be of interest in case you are thinking about these surveys. Usually when you're planning these lines out, you plan them out in a grid with gaps for any kind of infrastructure. So here you can see all of these gaps here. We're avoiding buildings, highways, electrical infrastructure such as large power lines, and then any restricted airspace. So the helicopter is not going to fly over any buildings, urban areas, and then anywhere where you would have interference or noise, which would be from power lines, railroads, buried pipes, things like that. So ideally, this is applied in rural areas. That's the ideal location, is where there's absolutely nothing. And so this was actually a challenge in the Salinas Valley because, as you can see, there's a lot of, as people refer to it, cultural infrastructure. And so here you can see in the planned flight lines, there are quite a few gaps. And then the as flown flight lines are here overlain in white. And you can see in general, the helicopter tracks along those lines very, very closely. In some cases, the helicopter has to deviate. And that's either because of safety, the helicopter pilot realized something that we didn't when we were planning the flight lines, or in some cases, they diverge to intersect existing data. And this gets back to those questions about ground truth and how you're tying into existing data. So it's so important to acquire these data in the same location as any good existing ground truth that we have, that we mark it on the map, and at all costs, we try to fly directly over those locations. And this is just an example of that, where you can see the as flown flight line. We made a last minute change to the flight line path and asked the helicopter pilot to fly over what is right here is a well that we wanted to fly over. And so you can see that white line gets much, much closer to this well here than the original orange line. So that
Another question, Ian?
Oh yeah, great.
What is the typical or preferred separation distance between flight lines?
Yeah, great. So in general, these lines that you see here, the closely separated lines, that spacing usually is between 150 and 300 meters. It's like up to 1,000 feet or so. And so that's for one of these denser, smaller surveys. For the larger surveys, oftentimes that's just not tenable because it would cost too much and it might take too long. So for example, this larger DWR survey across California. The approach is to fly in a grid of 3 kilometers by 13 kilometers. So that's much, much, much larger spacing. And the goal is really to have these kind of reconnaissance data set that people can use as a basis across many different basins to inform their understanding, and then to cite different locations where they might want to do an updated, more targeted study.
And one more question. What is a quote unquote quality geologic log for this application? Water well logs generally are pretty poor quality for most of the applications I've done.
Yes, that tends to be the case. So I guess the answer to that question is really as good as as you can get, because at the end of the day, if you're trying to fill in data gaps, you can only do as good as the data that are available are, I suppose. And so we make every effort to find lithology logs that were described by geologists, usually that were drilled for monitoring wells, nested wells. In some cases, the municipal supply wells, they tend to have better information associated with them. And they often have geophysical logs acquired, geophysical resistivity logs can also be a really fantastic auxiliary data set that you can use. So it's kind of, you take what you can get, but we always strive to look for monitoring wells that were drilled for scientific applications, and often, by state agencies. Those tend to have higher attention to detail.
And one more question, is the geophysical data processing program proprietary to AICOM?
Oh, no, not. There is a proprietary software. There's one that's very popular that's owned by a Danish company. But then there are also open source softwares. However, those are a little bit less user friendly. They're used more in the research space, and so you need to be, I guess, have a lot more experience to use them, or just know the people who are developing them, so that you can constantly barrage them with questions, that was my case. And here I'm just going to show you a really quick video that will show you here the distribution of these data kind of in action. So right now you're looking at, from a map view, you're looking at the geophysical data that have been processed and inverted. So now we're looking at estimates of the electrical resistivity. And up in the top right-hand corner, you can see the color scale here. Red is more saline, and blue is a higher resistivity, is fresher water. And so here you can see as we tilt the camera, we can get a slice into the ground surface. Now, just to remind you, we're looking below the ground surface, just projecting on top of a map for simplicity's sake, but we can get a whole ton of information about the subsurface by using this method. So here you can see in red, this is a wedge of salt water that's intruding below this fresher water. And this is part of the passive active saltwater intrusion that we were talking about earlier, where water flows down and into this aquifer and then flows back inland. So you can even see just from the data in a really spectacular way just how this is happening. So you get a much more intuitive physical understanding and confirmation of what's going on in the subsurface. You can also see that we're able to now get a better sense of the connectivity of the fresher water and the spatial distribution of that salt water. So here we're just slicing and just going back in space. And you can see here now, as we go up farther north, the saltwater extends much farther inland and in a much narrower band in elevation. And so this really just demonstrates the power of this method in order to you can see so many things and work so much with this data just from one acquisition. Let's see if I can get out of this now. Okay, great. Anna, how are we doing on time, by the way?
It is 9 after.
Okay, great. And so I should go until past.
I believe that's the time we had on the meeting. Yes.
Okay, yeah, perfect.
But Ian, since we've been asking questions as you go, I think you probably can go an extra 5 or 10 minutes if that's a good break point.
Okay, yeah, I'm happy to go. I can go as long or as short. I have plenty of material. So now that we've seen like a glimpse of the data, we can now drill more into what we can extract out of here, more quantitatively speaking. And so earlier I had mentioned that the resistivity is controlled by many different material properties in the subsurface. And so it was important that we're able to start extracting out, being able to have a confident interpretation by looking at a resistivity value, knowing for a fact that it corresponded to freshwater or saltwater or some other property. And the way that we approached this was by using borehole geophysical data that were recently acquired, along with TDS measurements that were recently acquired in nested monitoring wells across the region. And so here on the bottom, I'm showing you a histogram of the borehole resistivity values that we collected from 9 different boreholes across the study area. And so the resistivity is shown on a logarithmic scale on the x-axis, and then the count, how many values of those, so it's just the histogram shown in the y-axis. And you can see these different values are colored according to the salinity in the screened interval corresponding to where the borehole resistivity values were acquired. So any borehole resistivity values that corresponded to a screen interval where we had a total dissolved solids, or TDS, measurement of greater than 10,000 milligrams per liter, that's colored as pink. And then in yellow, these were TDS values between 3,000 and 10,000, and less than 3,000, excuse me, are shown in blue. And so those were our cutoffs that we decided on based on some EPA values of what could be potentially useful groundwater. 3,000 milligrams per liter is already too salty to drink. However, it's low enough salinity that it's considered a somewhat protected resource. And that's because it could potentially, without too much energy invested in desalination, could be cleaned up and used for drinking water. So it's a potential source of drinking water. And then on the opposite side of the spectrum, above 10,000 milligrams per liter is just such a high TDS value that it was kind of considered completely saltwater intruded. And for reference, 10,000 milligrams per liter is it's just under 1/3 the salinity of seawater. Usually seawater is around 35,000 milligrams per liter. So we were able to make these determinations based off of this histogram, these shaded regions, where we decided that it was we had a high confidence that those resistivity values corresponded to the corresponding salinity. So between less than 3 ohm meters, which is how we measure resistivity, less than 3 ohm meters corresponded to saltwater saturated sediment. And then over here on the far right side, higher than 80 ohm meters corresponded to unsaturated sediment. And then between 20 and 100 ohm meters, we considered this fresher water saturated. I say fresher water because, again, you can't drink this water necessarily just directly out of the borehole. And as you can see in the center here, where all of these the pink and the blue and the yellow histograms are overlapping, we weren't confident enough to make a determination. And so we just left this as the undetermined region where without any other additional data sources, without any other kind of lithology logs, without any other auxiliary information, we didn't feel confident enough to make a determination here. And that really, again, underscores the need for existing data for us to be able to pull apart these this really mixed signal that we end up with in resistivity. So now I'd like to show you some cross sections and how we're able to interpret them using these data. So on this resistivity scale, I have just underneath the saltwater saturated, fresher water saturated, and unsaturated, just for reference. And what we came in here into this project with from A to A prime is the cross section that we're looking at right here in the inset map. And so on the left is close to the coast. On the right-hand side of the cross section is farther inland. We're looking about 8,000 or 8 kilometers inland. And what we had as existing data were these 3 boreholes that were close to the coast that contained resistivity data, borehole geophysical data, with the same color scale up here. So we knew that close to the coast, there were things that were very, saltwater saturated. As you've tracked farther inland, there were some regions where there was actually quite fresh water, and then kind of a mix and a gradation going down to saltwater. And here in brown is the ground surface as you go from west to east. And before I show the AEM data that we acquired, I'm just prematurely graying out the region below the depth of investigation. I had mentioned that the AEM method can penetrate down to up to 1,000 feet below the ground surface, but that really depends on the resistivity of the subsurface itself. So if the subsurface is very conductive or it has a very low resistivity, the signal is eaten up really quickly. It dissipates quickly. And so you're not able to penetrate very deep into the subsurface that way. Conversely, if you have a very resistive subsurface, you'll be able to get information that descends very deep into the subsurface. So in this case, close to the coast, as we would expect, we had a very small depth of penetration that descended about 60 meters or so. And then it gets deeper and deeper as we move inland and things become presumably less conductive. So this was the state of our knowledge of the region, of the distribution of resistivity here. And now I'm going to fill this in with the estimates of resistivity from the AEM data. So it's really incredible just to see how much additional context and information you can get by collecting these data. So you can see here, again, as I was pointing out earlier in the video, you can see this really beautiful saltwater wedge that is intruding beneath fresh water above it. As it happens, this is the 180-foot aquifer that we were talking about that has some fresher water in it. And then the dune sand aquifer, this very thin aquifer on top, has other fresh water inside of it. And then you can see right here, close to this borehole, where the blue in the dune sand aquifer and the blue in the 180-foot aquifer start to merge. And that's right where, as we know from some maps of the aquitard that separates the two, that's right where that pinches out. So this lined up exactly with what our hydrogeologic understanding of this area was. We were seeing that reflected in these images of resistivity. And so here again, pointing out the dune sand aquifer and the 180-foot aquifer. And this is kind of our understanding of what's going on here. That water flowing toward the coast, dropping down where there's no aquitard, and then flowing back inland. Now, moving up a little bit farther north, things change significantly up to the north in the way that the aquifer looks. And also, this was the area, as you can see from the transect B to B prime in the inset map. This is going right over the areas where it was suspected that there might be some vertical migration of saltwater from the 180-foot aquifer above down into the 400-foot aquifer. And so here, if we fill this in, we have, we're here going inland about 12 kilometers or so from B to B prime. You can see again, the resistivity in red shows locations where there's very saline water. And we can see that there are certain locations going from left to right where it seems like those the red band that's mostly horizontal starts to do a vertical turn. And so based on some mapping in the area, the estimated depth of the aquitard separating the 180 foot aquifer and the lower 400 foot aquifer was shown here in this dashed line. And then above that aquitard, 180 foot below the 400 foot aquifers. And so what we believe we're seeing here is evidence or reflection of the vertical migration of that saltwater from the 180 to the 400 foot aquifer, where the hydraulic head is much lower. So because of the pressure difference, there is a vacuum that's sucking down that saltwater into the 400 foot aquifer. Now, interestingly, what we saw in our data also, as you can see here in the shallow subsurface, there's also a significant long extended band of red here. And in this area, there are almost no monitoring wells in the shallow subsurface, almost none whatsoever, that we could find that were measuring total dissolved solids. And the reason for that is really because this surficial aquifer is not used whatsoever, because it has accumulated nitrates from agricultural applications. It's considered more or less a dumping grounds for those nitrates, and it's not used for any kind of beneficial water purposes. And it remains that way because below this red band, you can see a relatively blue band, and that is a thick, about 100 foot thick aquitard called the Salinas Valley aquitard that extends continuously, or so we believed, across the basin. And so people don't pay too much attention to this surficial aquifer. However, from these data, we saw that there's this really deep band indicating that there should be high salinity in this aquifer. And we asked ourselves the question, could this potentially be agricultural salts, as there was a question earlier? But based on the concentrations, it shouldn't be that a concentration of nitrates could be that high that we would see it come as such a strong signal here. So then we started asking ourselves, okay, well, is it possible that there's also saltwater intrusion into this aquifer? And it doesn't make a whole ton of sense because just based on the physics of it, in a natural system, there shouldn't be that much saltwater intrusion. In an aquifer that's not pumped whatsoever, it gets active rainfall, precipitation, and recharge every year. And so the only reason logically that there should be a significant amount of saltwater intrusion in that aquifer would be because there's a connection with a lower aquifer or some reason that the head is being lowered. And because people don't use this aquifer for any pumping whatsoever, it seems like it's a reasonable guess that there is some kind of connection points with the 180 foot aquifer that once again is acting like a vacuum or a pump that draws in this water, the salt water along with the fresh water, because of all the pumping that's going on in this region to support all the agriculture. And so this is not yet confirmed. The only confirmation we have is that we were able to find one monitoring well that contained TDS information in this location, not too far from this question mark on the cross section, which did have elevated TDS levels, and to the beyond the point where agricultural nitrate applications would be something that we would imagine. So this is an ongoing mystery, but is a really exciting demonstration of these AEM data, not just to investigate problems and questions that we knew, but also to uncover potential issues and uncover mechanisms that we didn't know even existed. And so that's, this is kind of the first pass demonstration of, what we were able to pull out of these data from this one survey that we conducted in the Salinas Valley in 2017. And so it's really an exciting thing that we're able to get that much out of it. The data are available for viewing by the public, by the agency that we partnered with to collect the data. And they're actively being used in development of a groundwater model in the area. And so it's really exciting that these data can not only help us with scientific projects, but also be a beneficial use for people who are actively planning for the coastal management of the aquifer here. And so based on time, I think I will leave it there because the second part of this is, the second part of my thesis is really just applying these data and integrating them into a numerical model of saltwater intrusion, which is super exciting. And this was actually the first time that was ever done. But I think that this is what I've shown here is a great, the first step, what you would do, and probably the most common use case of acquiring these data and the process of interpreting them. So maybe I'll just leave the rest of the time if anybody has any questions, or otherwise we can just end a little early. But yeah, I just wanted to say, thanks. Thanks to everyone for sitting and listening, and I'm happy to take any questions.
Thanks, Ian. That was really fantastic. We had a couple of chat questions come in that were kind of pinned to the back end of the presentation here. Dave Heidloff, did your question kind of get answered in the course of the talk?
Ian, for those of us who live in the Midwest, what is the size of a study area that we could consider before it would be practical? Is it 10 acres? Is it a square mile? And then what is the cost associated? Is it something that some of the people on the call might be able to employ on a private project, or does it really need to be scale in square miles? If you could give us a feel. Yeah,
so these smaller projects, so my project is definitely considered a smaller one, and maybe if you guys can tolerate the flipping through these slides, I'll just get back to the map of those flight lines to give a kind of a spatial understanding. So in this project, we collected 635 line kilometers of data over an area. It was about 100 square kilometers. It was let's see, it was about 60 square miles is what it was. So on the acre scale, I would say this is not probably the methodology you want to use, but really on the sub-basin scale. So once you start getting up into maybe 50 plus square miles, then it's something that will start becoming more of a benefit rather than a cost.
So like a township and range, not a square mile, just for relative size.
Right. Yeah.
Okay. Thank you.
And then in terms of the cost, so I believe that every company, it's going to depend on the contract specifically and who the cost sharing that goes on. I think some rough estimates. So I believe something on the order of $100 per line kilometer of data acquired, and maybe something between $3,000 and $6,000 for the mobilization, demobilization might be what you're looking at. And then the reason why it's extremely variable is because it depends on who's doing the processing and inversion of the data, going from the voltage measurements to estimates, these images of resistivity. If you have some capacity to do that in-house, you can probably save a lot of cost and keep it pretty close to that estimate. But then the processing and interpretation can add up to you know, another 50 to 100% of, you know, the cost of actually acquiring the data. So it can be certainly pricey. And so that's why I think the reason why it tends to be funded by public agencies is because it tends not to just be on a private single parcel of land. And it usually ends up being a government agency that has some jurisdiction over multiple regions where they have interest in all of them.
You were kind enough to share a couple of Midwest examples, one along the coast of Lake Michigan and up in Wisconsin. Are you aware of any other studies ongoing or planned for Illinois, Indiana area? Or
I know none. I don't know of any. I haven't reached out to anyone. I know about the Illinois project because I saw the lead scientist give a talk at AGU about the data that they had acquired, but I don't know of any. There's a good chance that there will be some. I think especially after this, the Wisconsin survey, especially, you know, based on what comes out of that.
Thank you.
Craig, do you want to ask your question?
Yes, I think Kathy and Wendy are probably on the edge of their seat, hoping that you'll say that you'll send in an abstract and speak at the Sacramento conference this year, because this would be just your Salinas Valley project. It would be just so well received, I think. Have you given any thought to that?
Yeah, I would enjoy submitting an abstract, certainly, and whether it's this Salinas Valley data or maybe even something that's ongoing with the like an update on the California project.
Yeah.
Not sure yet, but certainly would be interested.
I would even venture to say you could submit a couple of abstracts if you wanted to.
Yeah.
And they may or may not pick both, but certainly they would love to receive an abstract if you chose to submit.
Great. Yeah. It's a great conference.
Yeah, that would be great. We would love that. You're right.
Well,
Would you be able to comment on the potential for this technology to be used to evaluate the salt pile problem that we run into in the Midwest, where we have salt in piles that creates a saltwater plume in the groundwater, and I'm guessing that that concentrations can get fairly high and potentially in the range that you'd be able to detect. Has anyone ever used it that way?
I don't think so, because the only surveys that I know of that are actually in areas that receive snow in the winter are the Illinois survey, but that was mostly over the lake, and then this Wisconsin survey. But the Wisconsin survey was, yeah, it was done during the winter even. So no, I don't believe so. I really don't believe so.
Ian, Harvey Picorni here. Just first off, I want to say that the Monterey Bay study was just spectacular with the way the saltwater intrusion was shown on the animated graphic. Second of all, I have a problem with the word alleged, and it's my problem, not anybody else's. But when you mention alleged ground seawater, you kind of take away from the scientific view of what it is you're doing. Just the word itself. That's my only. It's a critique, if you will, but that's just that's just my opinion.
No, I appreciate that. I guess I don't know when I call it alleged seawater. Maybe I did when I was was that when I was talking about the intrusion in that superficial aquifer?
Well, no, it was right at the beginning when it was obvious the red saltwater plume was coming in, and you said alleged saltwater, and it was like, and it takes away from possibly takes away your message, especially if you're doing it on a public speaking thing and you got the public around. That's my only. I've done this before, so.
Sure. Yeah. No. Thanks for that feedback. Yeah. If I said
Anyway, but it was a great presentation. I really enjoyed it.
It looks like Ian may have gotten frozen here. Let's see if he comes back.
Hope I didn't freeze him out.
Yeah. You shocked him into silence.
Well, it shocked me. I have an issue with that word because they use it on TV all the time when the situation is obvious and they say alleged, and I'm going, but that goes along with the news in general.
Well, we'll give Ian another minute here to see if he can get himself unfrozen. I know that John had another question for the end here, so we'll see if we can get Ian back to answer that. It looks like Ian's dropped out. Let me see. Let's give him a minute and see if he dropped back in.
Come back in.
Yeah. Yeah, it looks like he's coming back in. Hey, Ian. I think you're muted now, but you're
Hey,
unfrozen,
everyone.
so that's good news.
Yeah, sorry about that. I just dropped out.
No
No,
worries.
I was just sorry. I was just saying, I appreciate the feedback. We didn't go out and verify any of these values. We didn't drill any boreholes to confirm after our geophysical data. So everything was an interpretation. And that's oftentimes the best you can do without going out and verifying. But yeah, no, thank you for the feedback.
And John, would you like to unmute and ask your question?
Yeah, Ian, great talk. I really enjoyed it. I've just got a question about the sensitivity to thin layers. What do you think you can resolve in terms of the surface layer? And then how does that change as you go deeper in the section?
Yeah, so at the very surface, the concept of resolution, it's a tricky one because this is a diffusive measurement. So in general, when people talk about resolution, the small scale to which you can, identify a feature, that tends to be on the order of about 6 feet, really close to the surface. So if you have something that's relatively close to the surface, you can resolve it down to the 6 foot, between 6 foot and 10 foot block.
Okay.
When you start getting down into the subsurface, maybe 300 to 600 feet down, then your resolution starts to become, on the scale of hundreds of feet. So it ends up becoming a really, definitely a diffuse measurement. I'm trying to see if I have a good example here from the slides, but maybe that gives you an idea of also what kinds of applications you might want to use this method for. You don't want to use it to try to find thinly bedded layers because you'll never find them. So here you can see this is all in meters, and I've just been kind of trying to say things in feet in general. But as you can see, really close to the surface here, these little layers are quite thin. And then if you just go, if you go down to this around like negative 100 meters or 100 meters, negative 100 meters elevation, then you're starting to see blocks that are, about 10 meters large. So we're talking like 30 meters or 30 feet, 35 feet.
Okay. Yeah, I know there's a contractor out there that's telling people that they can resolve with less, like about a foot at the surface. And I know that the Wisconsin Geological and Natural History Survey has been a little frustrated because they're trying to map the thickness of overburden in the like 1 to 3 foot range, and they just can't pull it out of that data. I mean, it's good data, it just doesn't have that sensitivity.
Yeah, that doesn't surprise me at all. If they're using the same method,
SkyTem.
Yeah, okay, it's a SkyTem system, and they, you can adapt these systems to have to optimize them for a better resolution in the near surface or a better resolution at depth, or be able to penetrate deeper. But I think, at the 1 foot scale, that's just incredibly thin for a method like this.
Yeah,
Because
okay.
basically when you have a transmitter and you have this current going around the loop, you have to shut it off as quickly as possible. And then you listen for a response. And the goal is always to be able to listen earlier and earlier and earlier, but there's too much, there are just logistical challenges to measuring earlier and earlier in that time, where you just can't extract anything out of the data for a certain period of time until the signal gets really clean. And that's basically how early you can listen to clean data is what determines if you can have really good high resolution in the near surface. And it's hard to pass, 3 feet or so.
Thank you.
Well, that's all the questions we had in the chat. Does anyone else want to unmute and ask anything before we go?
Hi, Ian. This is Sammy.
Hey, Sammy.
I just have a question about how easily accessible and usable you think the public data sets may be in the future. Is it something that would be easily downloadable and software would be readily available to view it and find whatever part you're interested in and then apply that to a specific project you're working on?
Yeah, so I can speak for the ongoing California survey that the goal is really public accessibility, that everything's going to be available in a nice format at every stage, whether you want to reprocess all the data yourself and create your own new maps, and that's more oriented toward the research side, or whether you want to take the product, the final end product here, the electrical resistivity maps, and plot them out. And in that case, they would all be available in kind of like a CSV or Excel kind of spreadsheet format, so that you could integrate plot them as depth sections or as shape files, so that you can just see exactly where the lines are, so you can take a closer dive in. For previous surveys, it really depends on what people found to be the right way to distribute that data. So in the case of this data that we have here, the way that it was published was as a kind of a 3D geologic model, using a publicly available viewer data. So it's called Leapfrog Geo, which some of you may have used or may use. And so you could just download the viewer and then download the file, and so you can play around and slice and dice and look at things in 3D, but you can't export anything. So you'd be able to locate and then kind of reference yourself and jump over to, maybe ArcGIS and then kind of figure things out that way. But you wouldn't be able to kind of integrate the data themselves. Going forward, though, we really, that's a great point, and public accessibility is so important.
I got one more question, and that is, how fast is the helicopter moving forward during one of these surveys? What's the speed approximately?
I believe it's close to 80 kilometers an hour is what it can do. And so, yeah, sorry I'm just half the time I'm spouting out imperial and the other half metric. It's just some things I just remember. Everything, all the work is done in metric. So what would that be? I don't know, something like 60 miles an hour.
Yeah, about 60, somewhere in there.
Okay.
That's moving.
Yeah, that's moving.
Well, if anybody has anything else, or Craig, maybe you want to close us out.
Yeah, I think so. But again, Ian, just a really superb presentation. It's so cutting edge.